Another way in which Python can help you do statistics or empirical analysis is by simulation. And we're going to look at two cases here. One is high school puzzles, and the other one is simulating statistical outcomes, meaning properties of estimators. Let's first look at this idea of high school puzzles. So when you were at high school, you always got these questions like, there is a dark cupboard, there are 20 socks in there, 6 of them are red, 14 are blue. You randomly pick 2 socks out of the cupboard. What is the probability that these socks have the same color? Now the thing with these high school puzzles is that our intuition is actually extremely bad to solve these things. We usually get it wrong. And here Python can help by simulating the process, programming it, then running the experiment, let's say 10,000 times, and see what the outcomes are. And once we see what the outcomes are in Python, we can form a better intuition and perhaps even find an analytical way of solving the problem. So in the notebook, we look at this experiment where we have a coin, and we throw the coin, so we get heads and tails, and we keep on throwing the coin. In the first experiment, so in experiment 1, until we see the pattern head, tails, head. And in experiment 2, we keep on throwing the coin until we see the pattern head, tail, tail. Oops. So the notebook gives a reference to a TED talk which explains the idea behind this experiment. But the question basically is, which of these experiments in expectation will last longer? And our first intuition may be that since head and tails are equally likely, so we're using a fair coin, both of these experiments will last approximately the same time. So in expectation, the length of the experiment should be the same. And of course the point is that this intuition is wrong. And one way to see that intuition is wrong is to simply to program it, and we'll take the first step of programming it in this video. So how can we program this? So the first thing that we need is a function which we call check, which compares the coin throws that we have, and we're going to program the coin throws themselves later on. It compares these to a pattern. And if they're the same, the function check will return true. If they're not the same, check will return false. So one important element here is what is the length of the pattern. Of course, in our case, it's going to be 3, but there's no need to hard code 3. We can simply leave it as a variable. So what are we going to return? We're going to look at this list coin throws. Then we're going to look at the last n elements of this. So remember when we did the slicing in an earlier video. So minus n means we're going back from the last element n steps. So in our pattern we're going to look at the last 3 coin throws. And the question is whether this is going to be equal to the pattern that we are looking for. So that's the first function that we need. Now the outcomes that we're going to be looking at, of course you could model these as 1s and 2s, but yeah, why? It's probably easier to model them as heads and tails directly, so we know what we're talking about and we don't have to worry whether a 0 was a heads or a tails. Then we're going to define a function waiting time. And the waiting time will be determined for a given pattern. So we give a pattern to the function, let's say head, tails, head, and then the function will determine how long it takes to actually find this pattern. So we start off with throws. This is going to be a list. And we're going to use from NumPy the function random and then choice. So we're going to choose from outcomes. And when we start, of course, we need to have at least the length of the pattern, because otherwise it's obvious that we cannot have a match. So out of outcomes, which is head and tails, we immediately draw, in our case, 3 elements. Then we're going to use while. And I'll explain in a second why we have while not. So we have this thing called throws, and we're going to compare it to the pattern. This is the function that we just defined, this function check. Throws append, be random choice, and again we're choosing from outcomes. Oops. And now we're going to return the length of this list throws. So what we're doing here is that we define a list throws. So we start off with 3 elements in our case, because it's the pattern we're looking for is head, tails, head. So length is going to be 3 of the pattern. So we draw 3 patterns. Then we see out of these 3 throws whether we already matched pattern. If we matched pattern, then check is going to return true, which means that not check is false, and we leave the while loop, and we're going to return the lengths of throws, and in this case that will be 3. If the throws that we have do not match the pattern head, tail, head, then check is going to be false, not check is going to be true, and we're going to do the statement in the while loop which says add to your list throws a new element out of outcomes. So now we only pick 1 element, not 3, we only pick 1 element, add it to the list throws, and we check again whether this new list throws, the last 3 elements of that list, actually match our pattern. If it does, we stop. The length of throws is equal to 4, so we needed 4 throws to get to this outcome. If this thing is false, then the while loop is actually true, and again we're going to add an element to our list. So now we want to know on average how long is this going to take. So waiting time only calculates it once, so chance plays a huge role in determining whether this was going to last for 3 or for 10 throws. So we want to repeat this experiment, let's say 10,000 times, so we get a bit of an idea of what the generic properties are. So we define a new list waiting times. So there's an S here to differentiate it from the function waiting time. And what we're going to do is waiting times dot append. So we start with an empty list. Now I'm going to add elements to it. So what I'm going to add to it is waiting time function. Now I'm going to give it the pattern that I'm going to be interested in, which is head, tail, head. And we're going to do this for I in range, let's say 10,000. So we're going to do this 10,000 times. And then what I'm going to be interested in is the average of these 10,000 repetitions of the experiment, waiting times. So now I can run this, that'll take a second. So when we run this, we see that for experiment 1, on average, you have to wait 10 throws before you see the pattern head, tail, head. Now if you go to the notebook, you can do the same with the pattern head, tail, tail, and you can see whether this second experiment takes longer or is faster than experiment 1 on average. And then you can start thinking about the intuition for the result that you find.